Hello everyone, my name is Krepstzul and I'll be presenting with Sam Grattan about research article that was done about the azeotropic distillation process for isopropyl alcohol dehydration. So just a little introduction, a 99.9% anhydrous isopropyl alcohol is desired to be used for raw materials for paint and ink products. And of course, there's a common solvent in many chemical industries. The problem with getting such a pure IPA is that IPA forms an azeotrope with water at 87.8% weight percent and around 80.4 degrees Celsius. And you can see that liquid mole fraction diagram on the right for the azeotrope. Therefore, this means that pure IPA cannot be obtained via conventional distillation due to when azeotropes are boiled, the vapors will have the same proportions as the liquids, and a conventional distillation column would need an infinite number of trays, which is just not possible. So moving on, an azeotropic distillation will have to be performed. This is when an entrainer is added to a binary mixture, which results in a ternary phase equilibrium diagram, which you can see on the right side. In this case, benzene was selected as the azeotrope breaking agent or the entrainer to be mixed with the water IPA mixture and allow for a full distillation of pure IPA product. So how is this pure IPA obtained? So in a column, it would be obtained at the bottom of the column by condensing the overhead vapor streams close to the tertiary azeotropic point, which has to be below the 3 binary azeotropic temperatures. So the azeotropic temperatures of benzene water, water IPA, and benzene IPA, which it is, making benzene a good entrainer for this distillation. And just looking at the liquid-liquid equilibrium diagram, we can see that highlighted in red. Only mixtures entering in this region, so region 2, will produce the IPA product.
So azeotropes are algebraically defined as having a species with a equal liquid and vapor mole fraction. Because of this, the liquid activity coefficient can be related to the saturation pressure and total pressure of the species, and a unique graphical representation can be developed between the species, as Jan was demonstrating. So to determine the activity coefficient for this tertiary mixture, the NRTL liquid-liquid and liquid vapor interaction model were used by the team. They were able to optimize the vapor liquid equilibria interaction parameters for the IPA water and IPA benzene systems using the bubble point temperature and vapor composition at a constant pressure, and the liquid-liquid interaction parameters for the water and benzene were regressed with experimental data. So for the overall process, it has 3 columns, as you can see, but the second column is where the magic of the azeotropic distillation happens. For the first column, we see a typical extractive distillation. A stream of dilute IPA is basically purified to its maximum concentration, which is the azeotrope, through a typical extractive distillation process. Then in the second column, we have the addition of the entrainer, which is benzene, and that allows for a nearly pure stream of IPA to separate from the bottom of the column. At the top of the column, the vapor fraction is refluxed back into the upper phase, and the liquid that condenses is decanted and stripped in the third column. So that would separate some of the water from the benzene and IPA and allow a more concentrated recycle stream to enter into the upper phase and continue the reaction. So yeah, thank you for listening to our video, and I hope you can experience some of the cool azeotropes that we got to learn about. So yeah, thank you.